Welcome. In this one, I'm going to show you how to find derivatives of the form a to the x. So this is our function a to the x. I'm going to differentiate. But I'm going to show you how to use a common trick that says rewrite that in terms of base e, because then the rule for base e is well known, well studied, and easy to apply. Before we get to that though, I need to explain a fundamental relationship. So the next couple minutes will be a visual insight into something that you very likely have seen before, but I'm going to present it in a slightly different way, just to tease out this essential concept. I'm going to draw a vertical axis. This is my y-axis as usual. Let me zoom in here. I'm going to have a horizontal axis going this way, and then this. So this is going to be y, this is going to be x. And then I'm going to draw in the natural log function, which looks like this. With that in place, we're going to unravel, or rather open up a whole world. It's something that often is taught in a kind of indirect way. So take a look. For example, in this context, imagine this is a particular value of x. Then you plug it through the curve and it goes out over here on that side. Because this is the ln function, that means the output on the y-axis over here, that is the ln of x sub 0. That's what that means. It's this ln of x sub 0 is just a fancy way of writing y. So y equals this. It's just a y-coordinate at this point. And here is the next trick, so to speak. When you deal with functions like ln, its inverse, as you probably know, is e to the x. The only issue is you're always shown, here is the line y equals x, reflect across the line, draw it that way. When you read the graph this way, from the vertical back down to the horizontal. We can do that. We can read graphs both directions. When you do that, essentially what we are looking at is the following: e to the x. Why do we want to know that? Because it turns out that you really need just one graph, and depending on how you read it, you're either reading ln x or you're reading e to the x. That's all you need. Once you have that understanding in place, here comes a way of rewriting expressions that look like this. For example, e to the ln of x equals x. Why is that the case? Think about this for 1 second. So imagine that we do the following. We grab an x from here and we feed it into our function. So it's going to go this way and then come out over here. That output there will be ln of x. If you read that same graph now from the vertical back down to the horizontal, that's as if you were exponentiating. So basically it's as if you were doing this. But that means, in terms of the graph, that the following magical step occurs. Then it's as if you were basically reading it from here to here and then back down to x. And that's why you cancel basically this with this, and all that remains is x. Once we understand that e and ln are inverses, then it tells us that numbers like 1/2, the humble 1/2, can be written equivalently as e to the ln of 1/2. It tells us that things like this, that for example number 2 is equivalent to e to the ln of 2. Because if you wanted to, you could cross off this with this and get back to 1/2. Cross this off with this and get back to 2. That's a key understanding. We're going to make use of that when you do our derivative. I love this step. Take a look. I'm going to write this as dx, and then here I'm going to say e to the ln of ax. Why would I want to do it that way? I don't have to memorize a separate rule for a to the x, and on top of it, I just know the rule for ex, which is quite easy. Remember back that the derivative of e to the x is e to the x. So here I'm going to differentiate. That rule states you copy everything that you see, so e to the ln of ax, and then you just multiply by the derivative of the exponent, by the chain rule that is. So that's going to be the derivative of ln ax. Remember that ln a is a constant because a is a constant. X is the variable here. So it allows me to pull the ln a outside, copy the e to the ln ax, and then when you differentiate this portion right here, that's just 1, so that goes away. And this is our derivative. The master stroke occurs when you realize that because e and ln are again inverses, you can basically cross this back off and then copy the rest of it just as ln of a, bring the a down to the base and keep the x in the exponent. That's it. So this then becomes our derivative, ln a times a to the x, right here. And you do that simply by using the inverse functions e and ln. Imagine that this is 2 to the x. So this would be the following. If you wanted to do it with e, it would be e to the ln of 2x. You differentiate using the e rule, so that's e to the ln of 2x times the derivative of the exponent, which is just ln of 2. And then you realize that these are inverses, so they basically cancel off. You just copy the 2 straight down to the base. So you end up with 2 to the x times ln of 2. That's it. Obviously, once you've done this enough, then you very likely can remember the rule, but I personally still think this is a good way of doing it. So here's the derivative found using rewriting. Thanks so much. Please leave a like, it all makes a difference.